Actually, there's a problem with your mic.
Better?
Yes.
Yep.
Okay, great. I lost the video, the recording from that first part. So just so that anybody who's listening to this video right now, we went over vector kinematics and we describe a position vector, the position of a trajectory of motion using this vector, this position vector from an arbitrary origin, and then we could calculate the displacement and all its properties accordingly. And that's where we left off, and it leaves us to projectile motion. So what happens with projectile motion, right? So let's, in a simple case, it's almost like it's like free fall motion, but now you're given it a velocity in the x direction, right? So in this case, let's assume that we're on a hill and we throw this ball, horizontally. So that there's no velocity we don't give it any initial velocity in the y, we just throw it straight out. What will happen is that initially all its velocity will go in the horizontal direction over here, and then it will start picking up a y component due to gravity. It will start accelerating only in the y. So if I draw the ball's motion, it would look like something like this. And then over time, at each position, we could see this. If this is the velocity vector, it'll pick up velocity, right? It'll pick up velocity in the y direction, and the amount of velocity that it'll pick up in the y direction is the same as if we dropped it. And then so let's say if I drop a ball and throw it at the same time, will they? Which one will land first?
They'll land at the same time.
That's correct. They'll land at the same time. So the velocity in the x direction does not affect the velocity or the velocity and its position in the y. X and y are completely separate. And it's pretty amazing that this occurs, kind of, because when we break the vectors down into its components, the mathematics of it allows us to separate this vector into two separate components. And the world works in that fashion, right? Like if I push this marker this way, it's not going to start moving upwards, right? It's intuitively, this does not make sense, right? We've developed our way to kind of intuitively assume this whenever we move around, but we don't actually recognize that this is the case, until physics 101, right? So these will reach the ground at the same time because the velocity is only in the x direction, right? And this is true for no matter what situation that these velocities are separated. So if I threw a ball now from the ground, let's say I'm on the ground, and now I throw the ball at a certain angle, theta naught, right? That's the initial velocity. This is v0. What will happen is that it will make an arc, right? And we call this a parabolic trajectory.
Professor?
Yes.
I have a question regarding positives and negatives. So when you go up, we're going positive, and then when you go, or how does that work exactly?
You choose it for the problem. So right now, if you look, the y-axis is the positive is going up. But it depends on you get to choose which way is positive and which
Oh, okay.
direction is
So we
negative.
decide. All right.
You get to decide for the problem, whatever's easier. And you have to stay, as long as you stay consistent with the problem, it'll work out in the end.
Okay, thank you.
Just like where we choose our origin, it's arbitrary, right?
Yep.
That actually decides where we choose where we start from. Where's our origin, right? That's what would make it positive and negative. So in this problem, like let's say we had this guy up here, right? If we choose this to be the origin, this is our 0 instead of down here. If he's on a cliff, we choose this to be the origin, then traveling in this direction would be, or any position here would be negative, right? But we can also make it where this is, in the positive direction. You get to choose as long as it stays consistent. You get to choose the origin and your and which way is positive and which way is negative. Now, so if we throw the ball up, what will happen is that as we go near the top, it'll start the y velocity. The velocity in the y direction will slow down because it's deaccelerating, right? Velocity g is downwards in this case, right? So this would slow down, and then at the top here, the y velocity is 0, right? And it's completely in the x direction. Just like when we throw the ball upwards at the top, there's no velocity, and then it reverses on the way down, and then this is v, right? And so on and so forth. So no matter how hard we throw the ball in the x, it will stay in the air the same amount of time. We'll just extend this arc. Well, this arc would be much longer, right? If we give it more x component and keep the y component the same, right? Right, and then it reaches the bottom, and at the right before it hits the ground, it's the same speed as when I throw it. It's just that now the velocity is going downwards. The y component of the velocity is going downwards. X remains the same, of course, and then so the y is the opposite from what it began at. And we'll use the motion in each one of these coordinates to solve for the other one, which we'll see. So if we wanted to know how long this ball travels for, we would need to calculate how long it stays in the air. We would have to calculate the t just from the y component, and then we could just then use its speed to calculate how far it travels. And that's what we'll do. So in general, for this type of projectile motion, we will use a set of equations here. And this is from table 3.2. So for the x velocity, right, it's just vx0. And then its x position is just given by the velocity without any acceleration. Remember that we now, since the acceleration is 0, there's nothing else to this term. Now let me move this over a little bit. And then for the y, we would have now I'm going to assume that that going downward, downwards is negative over here, so negative g. If you ever have a problem, if you ever want to do a problem where you make going downwards positive, you just have to reverse the sign. But we're going to assume that going downwards is negative. All right. And then the y position is given by the full kinematic equation now for position, which is, I should have that, minus gt squared, right? And then we also have this, the final y velocity squared minus 2g y naught, the distance that it travels. So these are the equations that we'll use to describe any sort of these projectile motion problems, where we give it some initial velocity and the only thing acting on it is gravity. And that really defines what a projectile motion problem is. So let's go back to what I was saying before about throwing it off the cliff and actually calculate how long it takes to move. So we throw this ball at some initial velocity, and we'll just read the problem from the book. So a movie stunt diver on a motorcycle speeds horizontally off a cliff at 50 meters off a 50-meter high cliff. How fast must the motorcycle leave the cliff top to land ground level 90 meters from the base? So we want the motion to be 90 meters. So this will be 90 meters. And we need to calculate the velocity, the initial velocity. I'll write Vx because we know that he just travels horizontally off the cliff. He's not on a ramp, right? So the first thing to do is draw the diagram, which we did already, right? Then we decide what our coordinate system is. So where do we want our coordinate system to be? Where do we want our zero? To make this problem as simple as possible. So if we look at it, we want it to go down 90. So this distance is 50 meters, right? And if we look at the equations, how can we simplify it? By choosing the origin. If we choose the origin to be down here, we're left with these initial x positions, right? So the easiest way to do it is to set this as our origin. So this is our origin. And this means that we are traveling a negative, the displacement is a negative 50 meters. Okay? Now that we chose the coordinate system to simplify our equations, now let's look at our equations and see what knowns and unknowns we have, right? So these are our equations. We wrote it down already. What do we know in this problem? We know, so let's start with x. We don't know x naught. That's what we want to calculate, right? This is what we want. We know x0. I'll write x naught, even though it's the same because it doesn't change. We know x0. He goes off the cliff at a height of 0. All right. This is our origin. Let me write it. All right. We know that. We don't know t. Right? Now let's look at our bank of equations. What do we know in the y direction? Do we know its initial velocity in the y direction? Anybody? What's its initial velocity in the y direction?
It's 0.
Exactly. We know g. And then here we'll just use 9.8 because we included the minus sign in the equation. So I'll just write g is equal to 9.8 to be consistent with the problem, right? What else do we know? We know what?
The distance it can travel.
Yes. I'll just write it as y minus y0. And that's negative 50, right? So now, let's see. How many unknowns do we have? In this?
We also know x, right?
What?
We also know x.
No, we
98.
do know. It's 90.
Oh,
Yeah, let me write that down. I didn't write that down.
the video's about to end.
Okay.
We don't know the time and the velocity.
You don't know the two unknowns, right? You don't know the velocity, which is what they asked for in the problem, and we don't know time. So we just need two equations here, right? And so this is one, of course. And then the other is